welcome to this lecture. In this lecture we will start basically continue our discussion of queries which we have posed in the beginning of study of say system of nonlinear equation. So, second very important problem or question is that if we have an equilibrium solution of a system of nonlinear equation, that is x dash equal to f dx, then we want to know that if we perturbed our equilibrium solution, then what will happen. It means that whether the equilibrium solution will be regained or we have some completely different solution possible, whether the solution will tend to 0 solution or solution will be unbounded solution. So, that the discussion based on this second query we want to discuss in this particular lecture here. So, here we consider the second question of which is related to stability of solutions of a given autonomous differential equations, that is say x dash equal to f of x, and let x equal to phi t be a solution of autonomous differential equation x dash equal to f x, and we are interested in determining whether phi t is a stable or an unstable solution. So, this is the problem which I wanted to discuss in this lecture, but before that we need to understand what do you mean by stable or unstable solution. So, first let us try to consider the stable solution. We want to suppose we perturb the solution by a small amount, and the solution the new solution, that is the when we have a solution we perturb the solution, and now we look at the future behavior of that perturbed solution, and if the perturbed solution will remain close to the original solution, the unperturbed solution, then we say that our solution, unperturbed solution, is a stable solution. Otherwise we call that solution as unstable solution, or in other word, every solution psi t of this system x dash equal to f of x which start sufficiently close to phi t at t equal to t naught must remain close to phi t for all time t greater than t naught. So, it means that suppose we have a solution, say this solution, so we call this as phi t, right. Then consider a solution, say some other solutions, let us say psi t, which start very near to this, that is only this difference, and if it will remain almost like this, then we say that solution will be stable solution. But in place of this, if we have a phi t like this and if we have a psi t like this, and it will go say away from this phi t, then we say that our phi t solution is an unstable solution rather than stable solution. So, this is an intuitive idea. Let us write down the definition of stable solution or unstable solution in a precise manner, that is in term of mathematical language. So, the definition goes like this: the solution x equal to phi t of the system x dash equal to f of x is stable if every solution psi t of 3 which start sufficiently close to phi t at t equal to 0 must remain close to phi t for all future time t. Now, here we need to define what do you mean by close, right. So, to define closeness in terms of mathematical language, we need to define the distance function, which we have already discussed. The distance function in case of vector valued functions is given by the norm of the that function. So, here in mathematical terms, the solution x equal to phi t of 3 is stable if for every epsilon greater than 0 there exists a delta. Of course, this delta will depend on the value epsilon, such that the phi j t minus psi j t minus phi j t norm of this is less than epsilon if norm of psi j t naught minus phi j t naught is less than delta. So, it means that if at the initial point if they are close by, then after all future time, that is t greater than equal to t naught, they remain close in this sense, that norm of psi j t minus phi j t is less than epsilon for all t greater than equal to t naught, and for all solution psi t of your x dash equal to f of x. Then we call phi t as a stable solution, and if it is not happening for at least one solution of x dash equal to f of x, then we call our solution as unstable solution rather than stable solution. So, it means that for one, if you want to check for say stability of one solution, that is phi t, consider all the solutions of x dash equal to f of x, and if they satisfy this, then we say that our solution is stable solution, x equal to phi t is a stable solution. Otherwise, if we can find out at least one solution psi t such that initially they are close in the sense here that norm of psi j t naught minus phi j t naught is less than delta, but this second inequality may not hold, that is norm of psi j t minus phi j t may not be less than epsilon, then we call our solution phi t as an unstable solution. Okay, so this is the definition in terms of norm here. Now here this norm is any suitable norm on R of n. So here as we have discussed, we have different type of norm, norm of 1, norm of 2 and infinity norm. These are the commonly used norm we are using here. So let me write it here that if x equal to, let me write it x1 to xn, then norm of x, one norm of x is nothing but summation mod of xi, right, and 2 norm of x is basically it is under root of say summation xi square, that is this, and infinity norm of x is basically say maximum of mod of xi. So depending on the situation we will use any of these norm, but here in particular the coming few slides I will prefer to use this infinity norm. You can use any of the norm, and so we already know a result from function analysis that in finite dimension spaces like Rn all the norms are equivalent. It means that the qualitative properties will remain unchanged. Quantitative properties may differ, but qualitative properties like stability will remain unchanged. Okay. Now let us consider one problem based on this, that in this problem determine whether the solution x t equal to 0 and x t equal to 1 of the single scalar equation dx by dt equal to x into 1 minus x are stable or unstable. So here we have say let me write it here, we have x dash equal to x into 1 minus x, and we already know that equilibrium solutions are given by the solution of x into 1 minus x equal to 0, or we can say that x equal to 0 will satisfy this and x equal to 1 will also satisfy this. So these are two solutions of this, and they are of course they are more than these two solutions, and we want to check the stability of these two equilibrium solutions. So let us first find out the solutions of x dash equal to x into 1 minus x, because if we want to check for the stability of x equal to 0 solution, it means that we have to check 0 minus psi t naught is less than delta, implies that psi t norm, basically here it is norm, is less than epsilon. So if for every epsilon greater than 0 they exist delta greater than 0, such that this is happening whenever this is happening, right. So it means that we need to find out this should be true for every other solution of this system x dash equal to x into 1 minus x. So let us first find out solutions of x dash equal to x into 1 minus x, so that we can work with the definition of the stability solution, stability of 0 solution. First let us talk about the stability of 0 solution, then we can talk about the stability of solution x equal to 1. So, let us first find out the solution here. So, here we have x dash divided by x into x minus 1 equal to minus 1, that for simplicity I am writing. So, it is let me write it here x, and it is x minus 1 dx equal to minus dt. Now, here I can write it x minus 1 minus. So, it is x minus 1 minus x, it will give you minus 1 and it is minus 1. Is it okay? So, it is the solution here, let me write it here plus. Is it okay? So, this is the system differential equation. Now, let us solve this, and if you solve this, we have ln x minus ln of x minus 1 equal to t, right. So, we can simplify further, t plus some constant, let us say you can write it say c here, or let us say ln c, you can write it. So, we can write down this as ln of x upon x minus 1 equal to say you can write it here c times here, you can, or you can write it here ln c into t. So, we can write down the solution like x into x minus 1 equal to c e to the power t here. Is it okay? So, solution can be simplified like this. Now, we want to find out the solution x t. So, let us simplify further. So, here we have I can write it here. So, this is c e to the power minus t 1 upon c minus let me write it here. So, it is 1 upon c e to the power minus t equal to x minus 1 upon x, that is 1 minus 1 upon x equal to 1 upon c e to the power minus t. So, let us say simplify 1 upon c as c. So, I can write it here 1 minus 1 upon x equal to some c1 e to the power minus t. So, where c1 we am writing as 1 upon c. So, I can write this as 1 upon x equal to 1 minus c1 e to the power minus t, or I can write it x as 1 upon 1 minus c1 e to the power minus t, right, and where c1 is some constant which can be determined using the initial condition. So, this is your arbitrary solution of x dash equal to x into 1 minus x here. Okay. So, now let us find out the behavior of say x ideally equal to 0 solution, where we want to check the stability of this solution. So, let us say that this C1 you can identify, let us say that what is the value of C1 here, let us say that x of 0 equal to some x naught. Okay. So, I can find out this as this is x naught equal to 1 upon 1 minus C1. So, you can find out the value of C1 here from solving this equation. Okay. So, C1 will be what? So, 1 minus C1 equal to 1 upon x naught. So, C1 equal to 1 minus 1 upon x naught. So, we can write it this is as x naught into x naught minus 1. So, C1 is, you can use this relation. So, it means that we are assuming that x naught is non-zero, otherwise we have to use some other equation. Okay. So, initial condition is like this. Okay. So, now we want to check the stability behavior of x equal to 0. So, here we want to apply this the definition that for every epsilon greater than 0 there exists a delta greater than 0 such that the here phi t minus psi t norm is less than epsilon whenever phi t naught minus psi t naught is less than delta. Basically, it is an epsilon delta game. You give us an epsilon and we need to find out a delta such that this happened. Now, here phi t is your 0 and psi t we have already obtained like this. So, it means that this reduces to what? This reduces to this, that the norm of psi t is less than epsilon whenever norm of psi t naught is less than delta. Okay. So, now look at the solution here and look at the psi t here. So, your psi t is 1 upon 1 minus c to 1 e to the power minus t. So, your psi t is 1 upon 1 minus C1 e to the power minus t, or I can simplify it further. I can write it e to the power t minus C1, and that is your psi t. I am writing it like this. Now look at the norm of psi t. So norm of psi t will be what? Norm of e to the power t divided by e to the power t minus C1, and we want to make this quantity small say less than epsilon, and we want to see. But if you look at here, as t tending to say going bigger than t naught, or say t is bigger than or equal to some t naught, where t naught is the initial condition. Here I have taken t naught as 0, that if t is bigger than 0 and for any given epsilon, I cannot make this quantity this inequality true. Why? Because at t tending to infinity, then e to the power t is tending to infinity. Is it okay? So this can be, if we take it means that I can consider like this, that if epsilon let me write it here, that as t tending to infinity, this value psi t, which is 1 upon 1 minus C1 e to the power minus t, if t tending to infinity, then this value is tending to 0. So it means that psi t is tending to value 0, psi t is tending to 1 as t tending to infinity, right. So it means that if I choose epsilon very small compared to this one, say 1 upon 5 say 50, then I can find out some suitable time t such that the norm of psi t is not less than this 1 upon 50, right. So it means why? Because as t tending to infinity, your psi t is tending to 1. Is it okay? So it means that for given epsilon, which I am choosing as 1 by 50, I can find out a time t such that norm of psi t is bigger than 1 by 50, because this should be true for all t greater than t naught, that is 0 here. So since it is true for all t, in particular I can take very large value of t, and we can choose very large value of t such that norm of psi t is bigger than 1 upon 50, right. So it means that here your solution say x t ideally equal to 0 is not a stable solution, because whatever be the initial condition, your solution psi t will not be bounded by arbitrary epsilon, which is less than 1. So it means that x t ideally equal to 0 is not a stable solution. Is it okay? So now let us look at one more problem, that is, now let us consider the problem of finding the stability of x t ideally equal to 1 solution. So in this case we consider this for every epsilon greater than 0, there exists a delta greater than 0 such that phi t minus psi t is less than epsilon whenever, you please remember this, whenever phi t naught minus psi t naught is less than delta. Okay. So let us first look at here. Now phi t is 1 here, psi t is given as 1 upon 1 minus C1 e to the power minus t, and we want to make this small, that is less than epsilon. So first look at this and then try to see. Then if you look at it is what, let me 1 minus C1 e to the power minus t minus 1 upon 1 minus C1 e to the power minus t. This we want to show that it is less than epsilon if it is possible. When you simplify, it is what, it is minus C1 e to the power minus t divided by 1 minus C1 e to the power minus t, right. Now if you divide by e to the power t, this is what, C1 upon e to the power t minus C1. Is it okay? So now now here we can simply say that as t tending to infinity, right. So as t tending to infinity, this e to the power t minus C1 is tending to infinity. So it means that this quantity can be made arbitrarily small for choosing very large or choosing sufficiently large value of t. So it means that for any epsilon, I can choose the t such that this quantity can be made less than epsilon. Is it okay? So, it means that this that for every epsilon I can choose any delta in this case, because here we are not getting any condition on this delta, in fact I can choose any delta. So, in this case I can find out an epsilon such that norm of phi t minus psi t is less than epsilon for all t greater than 0. So, in this case this is say coming out true. So, it means that x t ideally equal to 1 is a stable solution, but the x t ideally equal to 0 is not a stable solution. So, in this so what we have shown here, that for dx by dt equal to x into 1 minus x, your x equal to 0 is an unstable solution, while x equal to 1 is a stable. Okay. So, now look at the next example. So, here next example is determine whether the solution x t equal to 0 and x t equal to 1 of the single scalar equation dx by dt equal to minus of x into 1 minus x are stable or unstable. So, here we have just changed this minus sign. If you look at the previous problem, here it is plus x into 1 minus x, and here we have minus x into 1 minus x. So, if you look at here your answer is just reversed. Here we have look at x equal to 0 is unstable and x equal to 1 is stable, but here if you look at x equal to 0 is now stable and x equal to 1 is say unstable, which is earlier it was stable. So, just by putting minus sign here, your behavior is just reversed. And how we can prove it? And this can be proven like this. I can write dx by dt equal to x into x minus 1, right. So, I can write these as 1 upon x, x minus 1 equal to dt. Let me write it here, it is dx. So, I can write it here x minus 1 minus here and plus here. Is it okay? So, I can write this as ln of x minus 1 minus ln of x, I can put equal to t plus say ln c. So, I can write it here as ln of x minus 1 upon x equal to this t plus ln c, and you can write here x minus 1 upon x equal to c e to the power t, right. And we can find out this is what 1 minus 1 upon x equal to c e to the power t, or I can write it here 1 upon x equal to 1 minus c e to the power t, or I can simply say that this implies that x t is equal to 1 upon 1 minus c e to the power t. If you look at in previous, we have what? Here we have x t equal to 1 upon 1 minus c e to the power minus t, and here we have 1 minus c e to the power t, right. And now I am not doing, you please carry out that here just by changing this minus sign everything will be unchanged. For let me do it for x equal to 0 now. So, for 0 I need to look at only the norm of this x t, right, and we can find out this the constant c depending on the initial condition, I can say. So, we want to show that can it be made arbitrarily small. So, if you look at here, the norm of this is 1 upon 1 minus c to the power t. This we want to make arbitrarily small. So, as we already pointed out that as t tending to infinity, this quantity is very large now, right. So, c e to the power t is going to be very large as t tending to infinity, and that makes 1 upon 1 minus c e to the power t kind of a small. So, as t tending to infinity, this quantity 1 upon 1 minus c e to the power t is tending to 0. So, it means that I can find out for arbitrary small, I can find out the t such that this quantity can be made less than epsilon. So, it means that in this case, this is corresponding to the case of x t ideally equal to 0. So, it means that in this case 0 solution is stable solution, and I leave it to you that prove that x t ideally equal to 1 is an unstable solution. So, this I am leaving it to you. Now, look at the next problem. So, consider the differential equation dx by dt equal to x square, and in this case we show that all solution xt with x0 greater than or equal to 0 are unstable, while all solution xt with x0 less than 0 are asymptotically stable. We need to understand what do you mean by asymptotically stable. So, here right now we can understand that it is stable right now. Okay, so let us simplify dx by dt equal to x square. So, here your stability is depending on the initial condition, that if initial condition is positive non-negative, then it is stable. If initial conditions is negative, then it is unstable solution. So, this kind of a stability we can say that it is half stable in the sense. Okay. So, now how we can simplify this? So, dx by dt equal to x square, I can simply find out dx upon x square equal to dt, and this is what minus 1 upon x equal to t plus c. If we integrate this, then I can get x equal to minus 1 upon t plus c, right. So, this is the solution we can easily find out, just it is a separation of variable case. Now, we must find out the value of c. So, the x of 0 is let us say call it x naught here. So, x naught, let me write it here, x naught equal to minus 1 upon c. So, this I can find out c equal to minus 1 upon x naught. So, I can simplify, I can write down the arbitrary solution of this as minus 1 upon t plus c, I can write it minus 1 upon x naught. Is it okay? So, this is your arbitrary solution. Every solution of say equation number 6 is written like this. Now, x naught is the initial condition, that is x0 equal to 0. Now, we want to prove the rest. So, here if you look at x of 0 is greater than or equal to 0. Now, if x0 equal to 0, then what you will get, then this c is not defined, right. So, I can say that in this case your this quantity is minus infinity, or we can say that xt is infinity. So, it means that if x0 equal to 0, then we have only solution which I can obtain from this is an infinity solution. But we can say that we have a, so it means that here your 0 solution is an unstable solution, because here what I am doing, I am just finding the norm of xt, right. So, it means that I am talking about the 0 solution, that 0 solution is unstable solution. So, we can easily check that we have a 0 solution of this. So, it means that the 0 solution is unstable. Now, look at the case when x0 is positive. So, if x0 is positive, then c is a negative value, or I can say that when x0 is positive, then this quantity is positive. So, it means that since t is starting from 0, t is greater than or equal to 0, then we can simply say that in particular if t is starting from 0 and if we take the value 1 upon x naught, since x naught is positive, so t will assume the value 1 upon x naught when it is starting from 0. So, it means that as t is tending to the value 1 upon x naught, then the value, then the xt is tending to minus infinity. So, it means that solution is going to be unstable solution, right. So, it means that when x naught is non-negative, then your solution xt is going to be very large, whether it is positive infinity or minus infinity, it is norm of xt is tending to infinity, right. So, it means that if x naught is positive or non-negative, then 0 solution is unstable solution. Now, look at the solution x0 is less than 0. When x0 is less than 0, then this c is basically positive solution, or I can say that here this 1 upon x naught is a negative, and hence t minus 1 upon x naught, it means that the whole thing is positive now. It means that for t greater than 0, we do not have any value of t for which this can be made 0, right. So, it means that, or I can look at like this, that here C is negative. So, it means C is positive now. So, it means that t plus C will remain positive for all values of t, and hence x will be taking minus 1 upon t plus C, and as t tending to infinity x will tend to the value 0, right. So, it means that I can make this quantity norm of x t can be made epsilon for arbitrary epsilon for choosing large values of t. So, it means that when x naught is less than 0, for given epsilon I can choose large value of t such that norm of x t is less than epsilon, right. So, it means that the solution is tending to 0 for large values of t, means as t tending to infinity solution will tend to 0. So, it means that norm of x t is less than epsilon can be achievable, right. So, it means that here in this case if initial condition is non-negative, then 0 solution is unstable, and if initial condition is say negative, then solution is asymptotically stable, means it is stable, and as t tending to infinity solution is tending to 0. So, this is the analysis of this example 7, and in next lecture onward we will discuss certain result by which we can easily find out the stability of a given solution. So, first we will discuss the case of linear system, and then we will consider the general nonlinear system of differential equation. So, that will continue in next lecture onward. With this I will finish this lecture here itself. Thank you for listening you. Thank you.